Hi guys, and welcome to today's video. In today's video, we're gonna see the different general purpose registers supported by our ARM Cortex-M microprocessor. We're gonna see as well how these registers are deployed by the C convention to properly manage and execute our C-based code. And finally, we're gonna see some demo using an STM32 microcontroller. So welcome to this video. Now, in terms of registers, ARM Cortex-M microprocessor does support two sets of registers. We have the general purpose registers ranging from R0 to R15 and the special registers like pre-mask and fault mask and so on. In terms of general purpose registers, ARM Cortex-M microprocessor does support 15 registers. R15 will be mapped to the program counter, and this one will be always updated with the address of the instruction to be executed. R14 will be mapped to the link register, and this one will be pointing all the way to the address of our return from subroutines or functions. R13 is our stack pointer, and this is banked between process stack pointer and main stack pointer. Then we have scratch registers like R0, R1, R2, R3. Then we have some other registers like R4, R5, R6 and so on. Those can be used for local variables. Those registers ranging from R0 to R12 can be divided into two subsets of registers. We have the low registers and the high bank registers. As you can see, those registers from R0 to R12 will be considered as our general purpose registers. Hence, can be used in combination with different instructions to access different memory areas in terms of read and write and so on. The other three registers, R13, R14 and R15, although in some use cases can be combined with some instructions to access some memories or to execute some specific set of instructions, but most of the time they were going to be deployed actually for the C convention to make sure that our program get executed properly. Hence, R15, which is the program counter, R14, which is the link register, and R13, which is the stack pointer, are quite critical to make sure that our program is executing properly. Now, the different ARM Cortex-M microprocessor registers will have certain meaning and use cases. Scratch registers ranging from R0 to R3 will be used to save the different input arguments and parameters for our C function call. R0 can hold as well the return value and result out of our C function call. Registers like R4, 5, 6, 7, 8, 10 and 11 can be used to save and hold the different local variables content invoked within our C function. R9 will, in the other hand, will have the base pointer used to initialize our data segment. R12 will hold the intermediate value between the different procedure call. R13, which is the stack pointer, will be always pointed to the top of the stack memory. That will be reserve the state of our C function call. Hence, it will contain most of the time the different local variables and input parameters of our C function. Link register or R14 will contain the return address of our C function. Hence, after we jump out or branch out of our C function, we'll go back to this address located in this link register. Finally, we'll have the R15 or program counter, which will contain always the address of the instruction to be executed by our CPU. Now, we're gonna see how those different ARM Cortex-M registers has been deployed by the C convention to properly execute our C function SSQ. Now, this is a basic C function that accepts two arguments and then returns single integer result. And this is the assembly code generated out of this C function. Now, our function accepts two arguments, x and y, and returns single integer result within this z variable. If we try to match basically the C code to the assembly code, we can see obviously that this first multiplication concerning the first argument x by x is matching basically the first line. This is mul instruction or multiplication instruction. The second multiplication, which is y by y, this is matching the second line. Then we are performing basically an addition. This is actually matching the third line. Finally, we are moving the result into the z variable. And as you can see, the z variable is stored within R0 register. And the final instruction, of course, is to branch out of our SSQ function. Here we are using the link register or the R15 register to branch out from this function to the return address, which is saved within this link register. Now, as you can see, the first multiplication is used against basically the R0 register. Hence, the first argument is saved within the R0 register. Second multiplication is matching basically this y multiplication. Hence, the content of y is saved within the R1 register. Now, the intermediate result out of this addition is saved within the R2 register. And finally, we are moving this intermediate result to this final result variable z, which is saved within the R0 register. And then we are branching out of our SSQ function. So as you can see, we have used basically the scratch register to properly manage the different AMP operation highlighted within this C function. So guys, this is our Keil MDK project, and as you can see, this is a C-based project. It has been developed and deployed for an ARM Cortex-M based platform. The hardware that we are using is an STM32 microcontroller. Right now, I have already compiled and loaded the binary into the microcontroller and started a Keil debug session. Now my code consists of a basic C function that accepts two input parameters, argument 1 and 2, and return a single result with type integer. This basic C function has been invoked within our main. And here I am checking the result. Now based on this code, I should be adding the argument number 1 to 2 and returning the result. Here the argument number 1 will have the value 1 and the argument number 2 will have the value 2. Hence the result should be, or the expected result should be 3. If the result is correct, I should end up here. If it is wrong, I should end up here. Now this is my function, and I have already set a breakpoint within the first line of our function. Now let's check out the assembly code. So as you can see, we are here. Now our function starts with a push instruction. This one, or let's say this routine, it is what is called prologue, or the prologue of the function. So we are saving the R7 within the stack area. Then we are allocating basically some space within the stack to save the first and second argument. Now based on this prologue code, the first argument should be in R0 register. The second argument should be in R1 register. And if I try to match basically the content of those registers to my C code, we can see clearly that the first argument actually is saved within the R0 register, and the second parameter has been saved within the R1 register. So far so good. Now if I continue the execution at assembly level, we can see clearly here that we are loading back from the stack area. So we are loading back what has been saved in early stage. And then we're gonna perform the addition. So far we can see that our assembly routine is using only the scratch registers, because we don't have a lot of local variables, and hence using the registers ranging from R0 to R3 are more than enough. Here we are clearly making the addition. Then we are saving basically the result that is contained within the R3 register to the stack. R7 is pointing as well to the stack, as you can see. So the same value as the stack pointer. Now this has been saved to the stack, then load it back. then we are moving basically this intermediate result to the R0 register. If you remember, the R0 register can be used for both cases. It means can be used as input argument as well as a holder or placeholder for the return value or result. Right now, it will contain basically the returned result. So this has been moved to the R0. Now this is the epilogue or the exit routine of our function. So we are already deallocating the space that has been allocated for the stack to save our input parameters. And then we need to return basically from our calling function. Here we are branching basically to the link register that hold the return address once we branch out of our function. And here we go. So we are here, and as you can see, so right now we are in the address after the branch to our C function, and the result is saved within the R0 register. As you can see, this will be saved within the stack because R7 now contains the same value as the stack pointer. Loaded back, then compared. When loaded back, it gets loaded actually to the R3 register. Now we are comparing to 3. As you can see, the content of the R3 register is matching basically the number 3, so the result is correct, and we end up here. So thank you.